Modernizing a data warehouse can be complex, but it doesn't have to be. Let me walk you through the methodology that we follow at Elastic for any data warehouse modernization project. Modernizing a data warehouse typically has three steps at a high level: assess, migrate, and validate. So you got to do the assessment of your current data warehouse environment. What is the current strategy? What is the current architecture? And then you need to come up with a plan, and you need to come up with the total cost of ownership and the architecture for the new system. And that's what the assessment phase is all about. Then comes the migration. And migration is not just picking up the old system and putting it in the new system. In most cases, in case of a data warehouse, it is a modernization effort because the old system might be something like Teradata or Netezza, and the new system might be something modern like BigQuery or Snowflake. And many of the data types and code and functions and procedures and triggers and so on and so forth from the old system may not even be supported in the new system. So it's mostly a modernization effort. You have to figure out how will you get your data to the cloud, to the new environment, and how will you migrate your code, whether it be stored procedures or triggers or workflows, things like that. How will you migrate that over to the cloud as well? And then the third step is validation and reconciliation of data at the row level, column level, cell level across the heterogeneous system, making sure that the data that was there in the old system and the data that is there in the new system, there is a consistency, there is a data integrity which has been maintained. So let's look at how we look at each of these three steps in a little more detail. Let's talk about assessment. While doing a data warehouse assessment, we often have to assess the inventory, what databases exist, how many tables, how many rows, how many columns, what tables, views, procedures, application hooks, tools, etc. exist as part of a data warehouse ecosystem. We have to do a volumetric analysis: how many rows of data is there, how many gigabytes, terabytes, petabytes of data is there in each database, in each table, etc. So you know what are your important tables from a volume perspective. And similarly, from a usage perspective, what are the most used tables, what are the most used stored procedures, and so on and so forth. You need to understand your data and code waste analysis. How much data has not been used in the last X period of time? So there might be stale data there might be orphan tables there that are no longer being used. You need to know what those are so that you're not wasting your data warehouse space, and you can get rid of them before you do the actual migration. Similarly, for code, there might be stored procedures and functions and triggers and other code elements that have been created over time but are not being used for many years now. And that is very common when you accrue tech debt over a long period of time in a legacy ecosystem. The third thing is code translation analysis. We are in the age of AI, and in most cases, people would at least use some level of AI to translate the code from a legacy data warehouse to a modern data warehouse, whether it be a managed system from a hyperscaler, for example, the BigQuery translation service, or it be an AI system that you write on your own using something like Gemini or ChatGPT or something else. It is important to understand the code translation capabilities of the system and how much of your code can be translated versus not. It is important to do dependency mapping and lineage tracking. When you're moving a data warehouse system, it's not just the database that is moving. There are upstream systems, downstream systems, systems that this data depends on, and systems that depend on this data. So when you're doing a migration of a data warehouse, you have to understand what are the dependencies on these systems and how would you map them into the new system. And using all of this, you need to understand the current solution architecture and build a new solution architecture. You need to figure out what data model updates you need to do, because in most cases your schema would change. For example, BigQuery recommends a denormalized table structure in many cases, whereas your traditional data warehouse might be a star schema or a snowflake schema architecture. So you need to understand what is your old architecture, what's your new architecture. Based on that, how would your data model change, and so on and so forth. And then based on that, once we have an assessment of all of this, we go ahead and prioritize different use cases, different data objects, and build a roadmap for the customer for the modernization effort. And this also results in a TCO, total cost of ownership analysis, and a business case analysis. So this gives the customer a chance to understand what would be the migration cost, what would be the cloud cost for the new system, and then what would be the cost of coexistence. Because it's not that you migrate on day one and that's it, you shut down your old system. There has to be a period of time when the migration is happening. It may be 6 to 9 months, sometime multi-year in case of larger ecosystems. And in those cases, for that period of time, both systems have to kind of coexist. So you need to understand what is the total cost of ownership considering those scenarios. For data warehouse assessment, sometimes we use solution accelerators. For example, Google provides a solution accelerator called the BigQuery Migration Service Assessment Tool. You can assess the current environment for many traditional data warehouses. For example, while migrating from Teradata to BigQuery, you can assess the current environment, export all the outputs into BigQuery and use it as a data studio report. So here is the dashboard that it produces, and we basically get what are the databases, what are the volumes in each of the databases and tables and so on and so forth, what is the usage analysis, what is the wastage, what are the query patterns, reports, upstream downstream systems, ETL jobs, schema conversions, query optimization suggestions, and so on and so forth. So based on this, you need to figure out, okay, now what do I do with this data? You can either migrate it or you can completely modernize the data. In migration also, you don't need to take everything with you. Half of it you might even retire. So for example, orphan tables or orphan systems, sometimes systems are put because there was a particular client that was very important and there were a bunch of customizations done for that client, but the client does not exist in the ecosystem anymore, but there is tech debt and there is old code and old data which still remains. So you can retire a lot of that data and the code base and not take it to the cloud. In other scenarios, you might want to retain some systems on premise because it makes sense to do that. In other cases, you would either rehost them or re-platform them into GCP or whatever is your target cloud environment. And in other cases, you might want to modernize certain workloads by either refactoring and moving it and improving it on the cloud, or completely replacing it or rebuilding it from scratch into some other system on the cloud. So, what to do with your system and how to build your modernization roadmap is the whole assessment exercise. And sometimes we do just the assessment as an engagement with some customers, or it can be part of a bigger engagement where we are doing the assess, migrate, and validate with the customer. Now that we've talked about assessment, let's talk about migration. Migration of a data warehouse typically has three main steps: migrating the data, migrating the code, and then migrating the governance of a data warehouse. Migrating of data typically has the data schema and the data itself. The data, when we talk about data, we are mostly looking at the historical data that needs to be moved to the cloud. But then you also have to figure out how will you move the incremental data to the cloud. So what schema you put together really depends on the system that you're going to use. So for example, you might have a star schema or a snowflake schema in your traditional system, but when you move to the cloud, you might decide to denormalize your data based on the BigQuery best practices. Similarly, once you're trying to migrate your data, how would you move your historical data? How much data do you have? Can you actually move it online, or do you need to think about an offline transfer? Or when you're trying to move it online, do you just dump it into the storage bucket and then trying to restore it? What kind of ETL jobs do you have to write for the schema conversion? All of that is taken care of during the migration of the data phase. Then comes the migration of the code, and code is basically all the ETL, ELT jobs that are required. Now the schema has changed, so you have to rewrite a lot of your jobs to accommodate for the new schema, but your data producers and your end data consumers might not have changed. So you have to make sure that you transform the data back into the format that they need to look at. All your reports and your upstream and downstream and dependencies and applications, they need to be changed, and we need to make sure that they work with the new system. And then the third step is governance. Super important. You need to make sure whatever security was set up in the old system, the new system is able to respect that, whether that be role based access control, identity access management, row level security, column level security, service accounts, key management. So, all of that needs to be taken care of in the new system, and we have to make sure that there is security parity from old system to new system, and then we improve from there on. And the migration doesn't finish there. You have to figure out now the coexistence and the cutover, right? Typically, a migration only completes when your legacy system is shut down. But before it's shut down, there will be a period of time when both systems are running in parallel because the migration is taking place. Half the systems are connected there, half the systems are connected here, and then you need to make sure that the data here and the data there is in sync. So we really have to take care of that, and then eventually make sure that we're able to migrate everything successfully and shut down the legacy system. All right, let's talk about what are the gotchas when doing code translation from the legacy system to a new system. The obvious one is syntax difference. The syntax in the old system and the new system may be very different. If you use something like generative AI, it can take care of a lot of that. Humans can take care of a lot of that, but you have to be careful because the old system might support certain syntaxes, but the new system does not support at all. Data type, code, variable names may be case sensitive in one system, but not the other. There are platform differences. For example, BigQuery doesn't have a concept of primary key or foreign key, but has nested columns. Different systems apply constraints differently to tables. Some systems don't have a concept of trigger, right? Many RDBMS have triggers, but BigQuery, for example, does not have triggers, and you have to implement that using either Python or JavaScript. Macros, another similar story. Many systems have macros. And when you move to BigQuery, that gets translated into a user defined function, and then you have to figure out the orchestration of that. Another thing which I don't mention here is indexes versus partitioning and clustering. So many other systems have indexes. BigQuery has partitioning and clustering. So if you're moving, let's say, from Teradata or a SQL Server to BigQuery, you have to figure out what your partitioning and clustering strategy is going to be. And accordingly, you have to make sure you design your system to make sure there is adequate predicate pruning. You have to figure out how to translate the non-SQL UDF functions. You also have to take care of quota limits when translating. Certain queries might need to be rewritten to make sure that they don't violate the quota limit for when you're running them on BigQuery. So these are some of the things that we have to take care of when translating the code from a legacy system to a modern data warehouse. One important aspect is when your new data warehouse gets data from various systems, right? It has to figure out what the schema looks like at various systems and build a canonical data model. That also happens in many cases when you're trying to modernize. You think, okay, I need to modernize these four systems, but they can end up in a single system, and this is what the new system should look like. In those cases, it is very important to make sure that you're able to map the schema, the fields from the old system to the new system. To do that, we use a concept called the metadata object mapper, or MOM as we fondly call it. It tries to understand the data schema of the old system and the new system and creates translation queries to translate your schema from the old system to the new system. So essentially, we're using generative AI to design our ELT process from the old systems, various old systems, into the new system by understanding the data schema in different systems. So this has been super helpful in modernizing data warehouses where your data sits in independent data silos, but now they need to be brought together in a canonical data model. Another thing that happens when your data is sitting in various data silos is the data itself, not the schema, not the fields, but the data itself might need to be resolved. So we did the metadata object mapper, but now we are looking at an AI based MDM or an entity resolver. And what an entity resolver does is matches the current data record. For example, if you have to do an identity matching, imagine a record for Matthew McConaughey. You know, if I ask 10 people in a room what's the spelling for his name, I can't even pronounce it correctly. I'm sure a lot of people will get the spellings wrong. And that is how the real world data looks like, right? A real world data is very different. Somebody might say Matthew McConaughey, others might say Matthew M or M McConaughey or Matt McConaughey, or different spellings of the same person. But you have to run your algorithms to make sure that you're able to resolve the same person across different systems so that you don't end up creating copies of that data while doing the modernization. So this is something that we really specialize in, and I will show you in a minute how we do it, right? The same thing applies to address resolution. For example, all of these addresses are actually the same address, but they're written differently because they're coming from different systems. Or product resolution. For example, in this example of an insurance data, right, all of these might be talking about the same product or the same product category, but because they're coming from different systems, they were described differently. So how do you identify the same product that they're talking about, right? So to do that, this is the pipeline that we have built. You will see that there is an entity extractor that extracts the entities, and then we have this big entity resolution module that resolves all these entities. And we might use an AI based embedding match approach to match the entities, or we might use third party data, for example, Google Maps data, to standardize the addresses and then try to match them. We might use named entity recognition in case of certain entity types that we want to extract using, industry leading named entity recognition models. Or we might use statistical models like the SoundX and the Levenstein distance and the fuzzy matching to resolve the entities. And once we've resolved the entities, then depending on the confidence score, either we enrich the entities and enrich our golden records, put them in our golden records in our final data warehouse, or if the entity resolution module says that there is a lower confidence in entity resolution, then we put them through a human in the loop and the human validates it, sometimes enriches it, and then puts the data in the golden record. So this is also an important concept when trying to modernize a data warehouse, where the data is coming from various systems and you have to put it together in a data model that has all your golden records. And now the final step, the validation step. And in validation step, I'll just talk about our 3R principle: reconciliation, restartability, and reprocessability, right? Reconciliation at the record level, at the cell level. We want to be able to compare the old system and the new system. That is extremely important whenever we design any job, any ETL, any ELT, any migration job, translation job. We want to be able to reconcile our data before and after to ensure data integrity. The next two things are restartability and reprocessability. If your job fails for any reason and you want to restart your job, you should be able to. And if you get garbage data and you want to reprocess your data, or if your job failed and you want to reprocess the old data again, you should be able to. So these are the three things that we keep in mind when designing validation. Let me know if this was useful, and please get in touch if you would like to discuss your data warehouse modernization strategy. Please subscribe to the channel.